Hey everyone, and welcome. Thanks for joining us today. And my name is Nigel Peard. I'm the sales manager for FLIR's range of science and research and development cameras. It's much appreciated you taking the time to listen through for around about 30 minutes today. And we're going to talk about a particular branch of thermal cameras, very specifically in the field of R&D and science. So one of the questions we may want to answer in today's webinar is, how does SLS technology solve real-world problems? Well, let's get started what we're actually going to talk about today. First of all, let's really review the basics. Let's get on the same page of the topic in itself. Now, infrared and the basic and fundamental theory, this is really an in-depth topic, and we could speak for hours learning about this and understanding the basics. So we're actually just going to cover the top level of how infrared works and how it compares to other infrared technologies. Then we're going to talk about what is SLS, and I'll try and define a little bit better what SLS is and how it compares to other technologies in the same field, other mid-wave sensor technologies, and also more older long-wave type sensors that are competing in this market. Then we'll look to some real-world benefits, and we'll look to a fun experiment that we coupled together with one of our CNR scientists over at FLIR by Dr. Austin Richards. And he'll showcase some of the advantages of mid-wave and long-wave SLS. Then we can finish up with a quick summary, lessons learned, and then we can dive straight into the questions and answers. So let's review the basics. So a few fundamentals here. Of course, infrared, it's a non-contact metrology technique. So in principle, it's safe for the user. It's non-intrusive, which means that with specialist windows, we can look into electrical housing, for example, using an infrared window. We can look into environmental chambers. We could even look into vacuum chambers, for example, and look at various devices under test. Secondly, it's two-dimensional. So unlike single point pyrometers or thermocouples, we actually see a really big overview of what's going on there. And if you're new to infrared, you can see a couple of images on screen there. One is literally a handprint from a table. And of course, the second is a rotating tire onto a surface. So you get an easy overview, and it makes it a little bit easier to compare as well. You may be looking at before and after, or you might be looking at different materials. So it's very easy to make a qualitative and a quantitative comparison in that sense. And finally, one of many, but it's almost real time. We can very easily look at stationary objects, and we can measure them very quickly. But it's also possible to record fast-moving objects and fast temperature changes. And these last 3 points, the measuring of objects quickly and the fast temperature change and cycle, these are interesting topics that we have to challenge ourselves in the world of infrared and when deciding on the right type of detector technology. So I mentioned at the beginning, this is focused for R&D and science, and infrared imaging is used in a whole broad spectrum of different applications, from aerial imaging to automotive. But today, when we talk of R&D and science, it's quite a broad topic in itself. At FLIR, we try to build cameras very specifically for this application field, and at the same time, we try to provide as much flexibility as possible. You can see a few examples here. These 12 examples, I mean, they're very broad in themselves. If you could read the writing, the first one is laser welding. The second one is friction stir welding. This is a really fascinating topic in itself. Here they weld together materials using friction, of course, but the temperature dynamics is extremely wide. We actually start around ambient, and the temperatures very quickly move to several thousands of degrees, which is a challenge for some types of infrared sensors. The last one on the bottom right, it's maybe not so clear, but this is a project where we were looking at a aerofoil inside of a wind tunnel, actually a hypersonic wind tunnel. Air is viscous in that sense, and what's important is that they can look to see when the flow over the aerofoil goes from laminar to turbulent, and this causes a different heat exchange on the surface. It can be very clearly seen with a high-speed infrared camera. No presentation on infrared would be complete without a short snippet of the infrared spectrum. So this spectrum is always fascinating for me when you actually look to see the amount of spectral energy across the different wave bands, all the way from the visible. If you look to see number 4 highlighted on the screen there, the very narrow band that our eyes, our human perception is sensitive to, typically around 0.4 to 0.7 micron. Very narrow band. But actually infrared, you can see they're highlighted. It's spanning around about 0.9 micron, moving up to around about 14 micron. So longer wavelengths than the visible, but shorter than radio, for example. Electromagnetic spectrum, the energy travels through space at the speed of light, of course, and like the visible, it could be focused, reflected, and also refracted as well. Now, this is certainly a good video to look over after the webinar. If you search it on YouTube, it's one of our science engineers, and it performs a very simple measurement, dropping of a golf ball and trying to look and understand the temperature of the golf ball itself. Now, here you can see the two different technologies. On the left, he has a cooled quantum infrared camera. We're going to be talking about this in a bit more detail. And on the right, he has what we call an uncooled microbolometer. But I'll show you the results of this right after discussing the two applicable technologies. So here we have cooled on the left and uncooled on the right. This is the typical naming. So it's cooled because we cool the sensor down to a cryogenic level. And it's uncooled on the right because, of course, we don't cool the sensor down. So cooled cameras, they work with different materials. In here we have INSB and SLS, which is obviously the core topic of today's webinar. And on the right, the uncooled, where we discuss microbolometer technology. Let's explore the engines inside these type of cameras in a little bit more depth. So cooled and uncooled, what do we have here? So if we look to the right, this is the core, or the engine, as you may say, inside of a microbolometer sensor. It's a small semiconductor device, and I mean, it's a thermal camera. It works in the wavelength of around about 7.5 to 14 micron, and this energy strikes the detector material and it heats it up, and this heating causes a electrical resistance. And this resistive change, if we were to simplify this process, we measure it and we process it into a temperature. We correlate this temperature using different black bodies and known standards. But effectively, this thermal sensor, this microbolometer, doesn't require any cooling. Now, if we look to the sensor on the left, here's our cooled, or our quantum sensor, or photoelectric sensor, as it's sometimes known. You can see that the first thing you notice, it's a little bit more complex. It has a cryocooler in there that's actually cooling the detector down. So the sensor is actually contained, it's actually in a vacuum seal or a dewar. And the cooling is necessary really for the operation of this semiconductor material. Typically the temperatures are around about 4 Kelvin. Some work at room temperature depending on this type of technology, but most modern cooled temperatures might actually operate in the 60 to 100 Kelvin range, really depending on the performance level. Now, the cooled sensors, I mean, they detect and convert light in the same way that common digital cameras work actually, but they use different materials. If we use this sensor without the cooling, we would effectively be blinded and flooded by its own radiating energy. The unit is physically working and warming, and this is why we need to reduce this level of energy. That's why we actually cool the detector down. Some of the drawbacks, of course, they're more expensive, relatively speaking, and they a little bit more power hungry because of this cooling. It takes 7 or 8 minutes sometimes to cool down to the cryogenic level needed for the camera to operate effectively. So let's look at the results of that video I promised earlier. Cooled versus uncooled. Here we have the cooled sensor, and now let's look to the uncooled sensor. Here what we have is a very simple application, drop-in of a golf ball. Now the ball is really not moving that quickly, but this is actually looking at one single frame. So this is just a snapshot of what's going on during that process. What you can see with the microbolometer is it's a 640 by 480 array pixel array. The camera can work to around about 30 Hertz, but here we're just looking at one single frame. Now this is what we call integration time, but you could relate this to a snapshot in time, the time at which the camera is being exposed. And one time constant here is around about 8 milliseconds, but we know if we're familiar with electronics, one time constant doesn't really represent the full picture. You need 3 or 4 time constants. So this means that we need to be waiting. This image is really around about 30 milliseconds. And as you see, as a result of that, the image is blurred. It doesn't really represent reality. Now let's look to the cooled sensor on the left-hand side. The sensor is taken at a much shorter integration time, 500 microseconds. And this represents reality. We know that that's pretty much the shape of a golf ball, and it shows it as a snapshot in time. So very short integration time. One important point to note there, which makes a big difference, which is worth highlighting, is look at the resolution of the cooled camera. It's a quarter of that of the uncooled, but the image still looks superior. So we'll learn a little bit more why the physics of where cooled sensors operate can be used to improve the quality and sharpness of an image. One further example, I should just explain what's going on in this image. This is the same device. What it actually is, it's a 3-bladed fan with a heater coil behind the fan. So you can see the cooled camera on the left. With this range, we operate the camera around about 66 microseconds or 0.066 milliseconds. So it's really quick. And the 2 examples on the right are 2 different microbolometers, and you really miss the fan completely. It's a constant blur of actually what's going on. That's really because the cooled camera has a snapshot type of technology, when actually the uncooled cameras on the right-hand side, they're what we call a rolling shutter. A rolling shutter, if you search on the line, there's lots of topics discussing this. Effectively, the pixel starts to read at the top left, and it starts to scan scan through the sensor until it gets to the bottom right. So you end up in a skewing of the image. It's very easy to see in the visual, but in the thermal, you don't necessarily see it, but it's actually happening. So we talked about different detectors and different materials, and let's look at a snapshot of the materials that we use today. So again today, let me check. Here we have the infrared spectrum, and of course we have the visible as described before, and we are moving into the mid-wave and the long-wave IR. Now these are the typical thermal bands like I described before, mid-wave operating in the 3 to 5 region and long-wave operating in that 8 to 14 micron part. And the microbolometer sits there also in that long wave. And here's our different types of materials. I won't go through all of these, but the key ones, if you see in the 3 to 5 micron, we've really got that INS-B sensor that we've been talking about. And in the long wave, we've got two core long wave technologies. One is the SLS, again, the topic today, but an older technology is this long wave MCT, mercury cadmium telluride. And we're going to be making some comparisons between this INS-B and this SLS and this SLS versus MCT, just to really show you how these technologies have progressed. So we know that cooled or quantum sensors produce clean, crisp image quality due to this global shutter. The image capture time or the integration time is a magnitude times better than uncooled counterparts. And it has a very low noise floor, and we could operate at very high frame rates. But maybe the real question is, how does this SLS compare to other technologies, and how does it compare to the midwave? So SLS, again, lots on the web about this, so just a couple of highlighted points. So it stands for Type 2 Strained Layer Superlattice, or T2SL for short. It was developed back in the 70s, actually, and wasn't till actually around about 20 years later the first high-performance SLS photodetectors came on the market. And they're produced by altering multiple layers of thin indium arsenide and gallium antimonide, quite exotic materials actually. The first focal planes were developed in around 2003, and since then they've experienced significant improvements, and the development continues. Personally, in the last few years, we've seen the SLS portfolio of infrared sensors from FLIR really start to expand and increase in their wave band as well. Let's look at this SLS spectral response. So what are we really looking at here? We have the photon, the normalized response on the y-axis here, and of course wavelength on this x-axis. And what we want to compare here is the new SLS technology on the right compared to the older MCT long wave technology on the left. Here you can see two cameras, two infrared cameras from FLIR actually. One is for reference a 7300, and on the right it's a newer 6701 SLS. Now, from the graphs, you'll see that the SLS has a much wider spectral response. It spans wider. Here it's about 7.5 to 10.5, but on some of our more advanced cameras, they operate a little bit further, nearly up to 12 micron actually. One of the noticeable difference, of course, on the left, the MCT, it has a little bit more quantum efficiency, around about 80 to 85%, versus SLS, which may be sometimes moving down to the 50% mark. But what does this mean in reality? Let's just look at a very basic example here. So A big feature of the SLS comparison to other long wave is it's very uniform and very stable. If you cycle the camera many times, a camera operating the SLS will typically turn on, like you see the image on the right hand side. And you can see this just by demonstrating this, looking at the two coffee cups. The image on the left is rather grainy, and it would need what we call a correction or a non-uniformity correction. This could be done with a black body, and often you need to put the black body in front of the sensor, which is a homogeneous source. And here we can improve and flatten the image. Now, in the lab, this might be okay, but often for field-based applications, it could be a little bit tricky and inconvenient. Also, same for applications where you may want to remotely control the camera from a long distance or inside of a test chamber, a hazardous area, or a government test range. And this camera here on the right hand side, this is actually from my demo stock. And this hasn't been corrected or updated in nearly a year, which is almost unheard of if you're familiar or you're listening and you're using this MCT type of sensor already. One big advantage of SLS is its integration time, and let me demonstrate that by comparing the SLS to the midwave. Our midwave camera operating in the 3 to 5 micron on the left, and our SLS camera operating on the right there. Both 645/12 type sensors with similar pitch, similar number of pixels. Now, if we look to the first temperature, you can see that on the SLS camera, it's operating in -20 to 150 is the typical dynamic range. It takes about 0.1 of a millisecond image capture or snapshot time or integration time, as I called it before. But if you look to the left on the midwave, it takes around 1.2 milliseconds, which may be quick, but it depends on the application. It's actually 12 times faster. So the obvious point here is a shorter integration time. But in some applications, that might limit you. Let's say, for example, you want to operate the camera at a kilohertz. Well, we know if we calculate frequency and period, if we want to operate at kilohertz, our images need to be taken at least every millisecond. So you can see there for that midwave camera on the left, we would struggle to operate that camera in that temperature band. But of course, with no problem for the long wave camera. And in some applications, frame rate is important to make sure that you're sampling and not missing those potential results. Here's a real world example demonstrating that. We have a couple of images, and what we have here is a tire. And when we test the tires, typical of rubber used on standard passenger cars, they actually don't get too hot. We don't want them to get too hot. They operate around about 40 to 50 degrees Celsius. Now, the image on the left is a midwave in-big camera. We have a calibration range of 10 to 90 degrees, and we want to capture about a kilohertz, so we have an integration time of around a millisecond. You might think, looking at the tire, it's a fairly clean image, but now we look to the image on the right where we used an SLS long-wave sensor. So unlike the midwave, the camera has a fast integration time, even in the low end of -20 to 150 degrees. And here you can see we can really freeze frame this image. I mean, if you look through the spokes of the wheel, you can see clearly you could get more reliable temperature data from that. of the brake pads or the brake discs. And if you look actually to the tire tread, it's not so obvious, but if you look in detail there, some tire manufacturers, what's important for them is to understand how this energy dissipates through the tread complexity. Just one important area that they are keen to understand. Again, back to a couple of comparison tables, but some interesting points here is the wide temperature bands. Let's look at this for the SLS and the long wave MCT. And the first thing, briefly, is again, if you look to the first line, the first temperature band, although both these cameras are working in the long wave, the SLS represents a newer, more modern technology. So the first band on the left is 5 to 50 degrees C. So it's very, very narrow before you start to need to change that integration time or shutter time. If you look to the right, again, we have a quite significant increase in the band. We can measure at least 100 degrees more in that first range. The next point also to look at there, where you see ND in the table, this is where we have to use a neutral density filter to reduce the energy on the sensor. And the main point being, we can use that much later on with the SLS technology. Let's just keep on the topic of this wide band, and I'll come to a few good real world examples in a few minutes. But here we're actually comparing this wide band to the midwave. Now this is more obvious. If you just to highlight, if you look to the first line on the right hand side, you can see that this is -20 to 150 degrees Celsius. So quite a wide band. Now to cover that in the midwave, you have to cover the first 3 lines. So you actually have to run the camera at 3 different integration time or shutter times just to reach that dynamic. And that's actually really just due to the physics. And let's look at that briefly. I think this is the last graph. But why do SLS give this wider temperature band? Let's look to the graph on the left, and this shows it's effectively the spectral emissive power of a target at 30 degrees. And the area under the curve represents the power in that band. And you can see from the shaded area, if you look to the left shaded area, this is midwave. It's very, very small. If we shift to the next shaded area, this is the long wave. So you can see that very clearly. We have a lot more power per meter squared working in this long wave band than we do have in the midwave. Now, if we look to the graph on the right, we see as the objects heat up, the peak represents the peak energy shifts to the left, and you see it starts to tail off to the right. So each of these curves here, if you're not familiar with Planck, it's an interesting topic just to Google afterwards. But just to repeat again, as you increase in temperature, the peak energy starts to shift to the left, and it tails off to the right. So the change in this band in the long wave is less dramatic, and it's more dramatic in the midwave. And this means that the long wave will allow us to work over a much wider dynamic range. Just a couple of examples. The example on the left is a MP5 machine gun, actually, very interesting. And on the right, it's an 81mm mortar round. Now, these are real-world images. So on the SLS camera in both these situations, it was set up for -20 to 150 degrees, and we had it operating around about 1 kilohertz on the left and a windowed down image to reach 2 kilohertz on the right. The main point here is that we can see everything that goes on in the image. So we can see the very hot gun. if you look closely on the left, you actually see the shells firing in the air. So they're also very hot, around about 160 degrees. But you also see the very cold contrast in the back. This might be interesting for range applications where you may want to measure something fairly hot, but have a reference source in the back, like the sky, for example. So a fun experiment. Now, I know what you're thinking. How much fun can you have with a plastic water bottle? Well, when you add a high voltage ignition and some alcohol, it could be quite interesting in infrared. So this is an experiment by one of our leading scientists, Dr. Austin Richards, and this is a flame jet. Again, you can use this, look at this afterwards, but you effectively take a 5-gallon plastic water bottle, drill a few holes, put an ignition system in it, and put a little bit of alcohol in there, and move it around to get the alcohol vapor. Maybe something not to try at home. But with everything set up, let's look to what type of apparatus we may want to add here. So here's our experimental setup. What we have here is 2 cooled cameras, one working in the mid-wave and one working in the long wave. Again, you'll see that the cameras themselves, actually the size and weight and footprint are actually identical. They're just working in 2 different complete spectral bands because of the detector and the readouts that we drop in there. So we sync everything together. That's perfectly normal for such cameras. We load up some factory calibrations, and we're going to run the cameras for around just under 600 hertz and do a burst recording of about 5,000 frames. And just as a reminder, this is where the cameras are operating. Here we have one in this mid wave, and again one in the long wave, just to give you that experiment. Now, hopefully you better see this video if I play it. And this is about 30 seconds long, so keep a close eye out to see what's going on. Okay, so something's happening in the bottle. Now we have a flame. Now in a few minutes it's going to extinguish the flame because of all the oxygen being used in the bottle. Then it creates a vacuum. And it pulls air in, and then it creates a secondary flame. Okay. Now this process actually took around 1.5 seconds. Let's look to that image in a little bit more detail. Now, here we see the frames early on in the recording. You see there are a lot of bright reflections in the left image. So the left image is the mid wave. Sorry, I should have mentioned that. The right image is the long wave. So what do we see? Firstly, we see some reflections from a space heater in the background, and that's actually because there's more emission and there's higher radiance in the mid wave for this particular band. So we're getting higher radiance from this space heater, and we're getting higher sensitivity to temperature change in the mid wave. You noticed before when we looked at those Planck curves, they were really steep in that mid wave part of the section. So although you've got more energy in that long wave band, you've got a lot more sensitivity to temperature change in that mid wave band. Now let's play the video back just at the beginning, but here about 40 times slower. Okay. While that's playing. Now this is 40 times slower, and you'll notice a big difference in how the water bottle actually looks. So since the water bottle is made from quite a thick plastic material, it's actually opaque in long wave. Therefore, you cannot see the ignition. It's if you look inside, you only start to see a very small subtle change, and then you start to see the gas and the flame evolve. So depending on the material, you may choose a spectral band that might be relevant. If you wanted to see through the material, you may look to the midwave. If you wanted to measure more the surface of the material, you could be looking to choose the long wave sensor. And secondly, see towards the end, there's a small puff of air after the ignition. This is actually the fact that there's the alcohol absorbs more in the long wave. So you see that in the long wave, but you don't really see that in the midwave. So it's quite fascinating just jumping between the two spectral bands, how you can visualize stuff and qualify this and make comparisons. And last but not least on this application, you see that the images when the flame is at its peak, they look a little bit different on screen. Now, firstly, the midwave on the left-hand side, it's much brighter. We have a lot of emission in water vapor, CO2, produced by the combustion process. But it's also the result of the smaller temperature range produced in the mid-band, lots more sensitivity to temperature change. But the midwave, that's also the reason why the midwave is so saturated. So this area in the middle where it really looks like there's not a lot of data there, well there isn't. The pixel is completely saturated. We actually convert, because of the saturation, you see we actually converted the level to counts there. But you see on the right hand side, there's only a very small level of saturation at the peak of the bottle. So it's brighter in the midwave because of this emission, and it saturates much sooner. And you can see there this ability to have this wide temperature dynamic is very useful. So long wave IR and SLS and working in the midwave, there's no better wave band to use. You saw there that depending on the wave band, it really depends on what you're looking to do. It's application driven. Let's summarize some of our findings now. So you can see here that in the long wave, we have much shorter integration time, certainly for the lower temperature band below a few hundred degrees. The temperature ranges are much wider and much better images for cold scenes. Also, you notice there is only certain phenomena that could be seen in this band. For example, the puff of alcohol in the vapor. And if we look to the midwave, again, working in the 3 to 5 micron, this isn't the only band. Midwave can actually operate in a much broader band in the 1 to 5.5 to 5.5 micron. But effectively, we have higher sensitivity to temperature change. That's why when we look to the floor in the last images, there was a lot more contrast there. It can actually see further if the air is humid. So maybe for long distance applications, that has some implication. Or because of the spectral band in the midwave, there are some very useful bands. For example, bands for certain lasers, CO2, for example. There's some absorption bands around the 3 micron mark. Midwave cameras are actually a little bit less expensive, and some of the lens, there's more lens varieties off the shelf. So just looking at the long wave and just coming to the final conclusions of the webinar. So here's a summary of some of those points again. It's a interesting material working in the long wave SLS, and it produces quite a niche in the world of infrared for R&D applications. So if we look to the long wave response, it could be material dependent or emission absorption. That might be the reason for looking to the long wave IR. it could be for looking at short integration times. Maybe it's to reduce the motion blur, or it's a high dynamic range, as I described there, in the broader thermal bands that you can actually see in one go. It has, if you're used to using MCT sensors, it has a better uniformity and stability, and again, a much more dynamic range there in comparison, and very good for cold temperatures. There's a lot of energy there in the long wave part of the spectrum. So in summary, the long wave detectors, it's an exciting evolution. It's been changing over the last few years, and really we're seeing it become a little bit more mainstream, and definitely a good consideration for a sensor technology. But certainly take time to talk with your local FLIR engineer or scientist to discuss that in a bit more detail. And by the way, the image that we see on the screen here, this is with a FLIR long wave. It's a 5.56 NATO round captured in flight. It's been fired from a M16, and it has a muzzle velocity of around about 3,000 feet per second. And they want to see how the fragments are looking in flight. So, absolute pleasure. Here's my contact details. Very welcome to get in touch with myself or locally.
Thank you, Nigel, for that. I think we have time to answer just one question. We have a couple of minutes. So I'll just go ahead with that. What are the typical frame rates achievable with mid-wave and long-wave cameras?
Good question. Actually, the frame rates are very comparable depending on either of those spectral bands. A lot of the sensors, to give you a couple of examples, X6900, which is a name that works in the midwave and is an SLS type sensor. A fairly high speed sensor might be 1 kilohertz, 1000 frames a second. And that would be operating with a sensor that is 640 by 512, which is quite typical. If you're and that's also the same in both bands. Now that can be windowed down, and windowing is a method where you may reduce the size of the image using less pixels to measure from, but it allows us to increase the frame rate of the camera. And if we increase that down into a fairly small letterbox, we can reach the typical highest frame rates of around about 32 kilohertz. If you're familiar with visual cameras, visual cameras work on a completely different type of technology, and these can run into hundreds of thousands of hertz. But infrared, we have to use certain exotic materials that are only working in this infrared band, and so 1 kilohertz for such a 640 512 sensor in both spectral bands, and 32 kilohertz, I would say, approximately for a window down type image. I hope that answers the question there, Sarah.
It does. Thank you, Nigel.